We began our study of chemistry looking at bulk properties or macroscopic scale of matter, solid, liquid, and gas. Now we'll look at the properties and implications at the microscopic level or invisible level, and the arrangement of atoms and molecules. In a solid, particles are close together and in a relatively fixed place. Liquids are particles that are close together, but they are freely to slide past one another. A gas, the particles are further apart. They have more energy and they move much faster. It's very important to review closely as you've read through the chapter. Look at the summary to recall the most important points of the chapter. The transition among phases is important and instructive to consider when thinking about atoms and molecules at the microscopic level. A transition of matter, as we see here, from ice in a very compact, arranged, orderly fashion, phase changes to a liquid where the molecules are further apart and can move past one another. And with more energy, the molecules are able to break away from the interactions among themselves and move more freely, transition into a gas. For a substance to change from a solid to a liquid, or from a liquid to solid, there must be enough kinetic energy to overcome the forces of attraction. The stronger the forces are between particles, the greater the energy required to make that phase change occur. In solids and liquids, the forces of attraction that hold particles in place are great. The forces vary from different types of substances. In this section, we'll explore some of those different ways the particles are arranged within solids and liquids and learn about the properties that result in their unique structures. When we talked about ionic compounds in chapter 5, we mentioned that the ionic formulas are really signifying a network or lattice, a rigid framework of the atoms. And because these interactions between the ions are so strong, it takes a tremendous amount of energy to disrupt these networks. The result that most ionic compounds have very, very high melting points. These substances tend to be very hard and very brittle. Elemental metals and alloys, which are combinations of elemental metals, usually form ordered lattices of highly packed atoms. Metallic atoms are loosely held, and their electrons are known to be very mobile, giving metals their characteristic property of being good conductors of electricity. While atoms are closely packed, the neutral metal atoms do not bind as tightly to one another. The opposite charged ions and Yeah, and these form and keep their ionic character. Because of this, the metal lattice is not rigid, and the shapes of metallic substances are usually easy to alter, giving metals their characteristic malleable behavior. And they are ductile, meaning they can be stretched into wire. Metals have moderately high melting points. Metals like iron, aluminum, copper are commonly melted and molded into useful shapes. Molecular substances, on the other hand, are discrete particles. Recall that these are held together with covalent bonds, not ionic bonds. Covalent bonds are the forces of attraction of a molecule. They are very strong, but the forces between the individual molecules are also important, and these are called the intermolecular forces. These are weaker than the bond forces, also called intramolecular forces. As a result, the molecular compounds usually have a lower melting point and lower boiling points. The exact properties of molecular substances vary widely depending on the strength of the forces that hold the molecules together. Some compounds contain covalent bonds, but can differ significantly from their molecular solids described previously. For example, elemental carbon exists in two primary forms, very different from one another, diamond and graphite. Both are examples of covalent networks, lattices of connected covalent bonds that form giant molecules in a diamond, for instance. Each of the carbons have 4 single bonds and are tetrahedral in geometry. The single bonds repeat infinitely, indefinitely in 3 dimensions, resulting in a rigid structure that are among the hardest and most durable substances known. In graphite, the carbon atoms form trigonal planal geometry, and these atoms are arranged in 2-dimensional sheets that can slide easily among each other, and resulting in a sulfur substance, as we know, graphite. Polymers are compounds that contain long chains of covalently bonded atoms. They are naturally occurring polymers, and they include cellulose, substance that makes up wood, proteins, starches, major component, staple in foods such as rice and potatoes, plastics, polyethylene, polyvinyl chloride, PVC, are synthetic polymers. The long chains of polymers are made up of small repeating units joined together by covalent bonds. Let's summarize these ideas. Ionic substances. These are hard, brittle substances. High melting points. Metallic substances conduct electricity. They're could be made by pounding or stretching into different substances. Molecular substances are composed of of discrete molecules and the melting point and boiling point. So these depend on the forces between the molecules, these intermolecular forces. Finally, covalent networks are polymers that have sequence of covalent bonds resulting in huge molecules. In solids and liquids, forces of attractions that hold particles together can be characterized as intermolecular forces. These vary depending on the different types of substances being considered. Let's talk about these intermolecular forces. The strength of intermolecular forces varies widely depending on the structure of the molecules. As a result, the molecular substances exhibit a stunning diversity of physical properties. Broadly, these can be divided into three key groups: dipole-dipole interactions, hydrogen bonding, and dispersion forces. As we saw in chapter 9, many molecules contain polar covalent bonds. In fact, this is the major types of covalent bonds. And depending on their shape, the molecules are polar, often have a net dipole, meaning different sides of the molecule have slight positive and slight negative charges. If the compound has a net dipole, the molecules that have those can stick to one another due to attraction of opposite charges, also called electrostatic attractions. This type of interaction is the dipole-dipole interaction. These interactions affect a substance's melting and boiling points. To illustrate this idea, let's consider these two flasks. The molecules in flask A have a molecular dipole, while in B, they do not, because the forces of attraction between the dipole molecules, the heat required to separate them is greater than those having no dipole. And this is reflected in a higher melting point and boiling point than those of nonpolar molecules, as in flask B. Let's look at this example and this effect. Carbon dioxide has no dipole. Sulfur dioxide has a small net dipole owing to its bent shape, and acetonitrile on the right has a large net dipole. The carbon dioxide transitions to a gas at a very low temperature of minus 79 degrees C. Sulfur dioxide boils at minus 10 degrees, and acetonitrile boils at 82 degrees. Notice that the larger size of the dipole, the higher the boiling point. Melting points and boiling points are handy ways to compare the strength of different intermolecular forces. However, we must be careful with our comparisons. Heavier molecules tend to have higher melting points and boiling points than lighter molecules. Let's consider these three compounds. The first, methane, has no dipole. Because of this, the methane molecules have very weak interactions among or between each other, resulting in a very low boiling point, minus 160 degrees C. The second compound, hydrogen cyanide, has a large dipole. As expected, it has a high boiling point of 26 degrees C, significantly higher. But the third, water, is surprising. Its dipole is smaller than the hydrogen cyanide, but its boiling point is much higher. This surprising observation results from the especially strong type of interaction or molecular intermolecular forces called hydrogen bonding. Hydrogen bonding is a special type of dipole-dipole interaction that only occurs between molecules containing HF, OH, and NH. And it's water that exhibits very strong hydrogen bonding effects. So what causes the hydrogen bonding? Recall that hydrogen atom contains only one electron. When hydrogen bonds to a highly electronegative element, such as fluorine, oxygen, or nitrogen, this one electron is pulled away, leaving a positive nucleus exposed. This naked positive charge attracts the negative poles of other molecules, such as a neighboring water molecule. And this attraction is relatively strong. But not as strong as the covalent bond between hydrogen and oxygen. Water contains two OH bonds, resulting in multiple hydrogen bonding interactions, causing water molecules to stick to one another. As a result, the melting point and boiling points of water are much higher than those of other small molecules. The interactions between water molecules are strong enough to hold some insects on. Insects can walk on water. The tendency of water to form these droplets and beads is also a characteristic of the strong hydrogen bonding. Hydrogen bonding plays a critical role in the chemistry of life, fundamental way that molecules interact, and the shape of huge molecules such as proteins and DNA. So what about covalent compounds? Covalent compounds that don't have dipoles. At first glance, we might expect that there's no interaction between them. However, this is not the case. Even though molecules with no dipole, there is a weak interaction, and this interaction is called London dispersion forces, sometimes simply called dispersion forces or London forces. London forces are related to dipole-dipole, but much smaller in magnitude. Even if they are shared, even though they're evenly shared, the electrons are constantly moving. And this motion produces slight fleeting areas of positive and negative charges, sometimes called instantaneous or temporary dipoles. These instantaneous dipoles are like ripples in a pool of water. On average, the surface of a pool level is even. However, at a certain moment, they do have peaks and valleys. These rapidly changing dipoles affect the surrounding molecules, and there are slight attractions that are fleeting. However, there are attractions, weak attractions. So let's summarize these three intermolecular forces: London dispersion forces, dipole forces in London, and hydrogen bonding. Of these, dispersion forces are the weakest, resulting in compounds having low melting point, low boiling points. Hydrogen bondings are the strongest, resulting in highest melting point and boiling points. When describing interactions, we focus on the strongest interactions between features of molecules. As an analogy, consider the light from the sun, the moon, and the stars. The stars are always in the sky, but their faint light is often blocked by the light of the moon or the bright light of the sun. In the same way, London dispersion forces are always present, but the effects are slight in the molecules that have dipole-dipole and hydrogen bonding interactions. Previously, we saw the properties of solids and liquids depend on the forces of attraction between molecules. Now, if we shift our attention to gases, these particles are spaced relatively far apart from one another. They move freely, interacting very little with each other. Gas particles travel in a straight line until they bounce off something or off the walls of containers. When describing gases, we often assume they behave as ideal gases. An ideal gas has two key properties. The volume of the particles is much, much smaller than the volume of the container. And two, the particles have no attraction for one another. When they pass by each other, they do not slow down. When they collide, they bounce off each other like billiard balls. When gases behave in this way, we can predict the behavior mathematically using some simple relationships between the variables temperature, volume, and pressure. We commonly describe gases by the pressure they exert on the surroundings. Formally, the pressure is defined as the force that is exerted divided by the area over which it is applied. We think of pressure as the push that particles exert on everything around them. Particles move freely in a box, they collide with the walls. Collectively, there's a tiny collision, creating a larger push. This is the pressure of the container. With a container like seen in this rural propane tank, the gas inside exerts a pressure that pushes outside on the walls of the tank. At the same time, air outside of the tank exerts pressure that pushes on the walls of the outside of the tank. Gas pressure is a normal part of our lives. The Earth's atmosphere exerts pressure, and that's essential to life. Subtle variations in atmospheric pressure causes wind and weather variations. Pressurized air in tires helps vehicles roll smoothly. The bounce of a basketball is caused by compressed air inside it. Air-conditioned systems rely on compression and expansion of gases under different conditions of pressure. And pneumatic tools, we use compressed air to produce powerful forces. A barometer is a device that's used to measure atmospheric pressure. Classical barometer is shown here. The device was a long tube inside a reservoir of a liquid, usually mercury. The gravity pulls the liquid down, creating a vacuum at the top of the tube. At the same time, the pressure outside air pushes down on the liquid. That pushes the liquid, the mercury inside the tube, up relative to the amount of pressure being exerted. Because of this, atmospheric pressure is often reported in millimeters of mercury, also called a torr. At sea level, the average atmospheric pressure is 760 millimeters of mercury, or 760 torr. It's referred to as standard pressure. The barometer works a lot like drinking from a straw. When you pull the air out of the straw, you're lowering the air pressure inside the straw. Because the pressure outside is greater than inside, the liquid gets pushed up to the top of the straw, the way that the barometer works. So why do barometers use mercury rather than less toxic liquid like water or oil? Because mercury is over 13 times more dense than water. Atmospheric pressure is enough to push a column of mercury at 760 millimeters, or 0.76 meters, into the air. If water was used in a barometer, the column of water would be over 33 feet or 10 meters high. Of course, there's many other designs of pressure gauges that we know of. Practical applications, sometimes referred to a gas gauge on a pressure tank, compressed air, basketball gauge, etc. Measuring pressure. There are several units that are used to measure pressure. We mentioned 760 millimeters of mercury, or torr. This is also equal to 1 atmosphere, which also equals 14.70 pounds per square inch, English units. And the international unit, 1 atmosphere, is equal to 101.3 kilopascals. And one more unit, 1 atmosphere, equals 1.031 bar. Not necessary to remember all those units, of course. If you need to, you know, refer to conversion tables or conversion factors. The pressure, volume, and temperature of an ideal gas relate to one another through simple mathematical equations. As we mentioned, these are called the gas laws. These are relationships that are very important in describing common gases, including air, nitrogen, oxygen, helium, acetylene, carbon dioxide. And we'll take a look at these relationships that have names Boyle's law, Charles' law, and combined gas law. Boyle's law describes a relationship between pressure and volume of a gas. According to Boyle's law, the pressure of a gas relates to its volume, and they're inversely related. That is, if the pressure goes up, the volume goes down, and vice versa. For example, if you think of an oxygen tank that on this firefighter's back, the oxygen is pressurized in a small volume, so it has high pressure. As long as the temperature does not change, the pressure times the volume is constant. Let's look at it as an example here. A commercial compressor stores 2.8 liters of air at a pressure of 150 psi. The air is allowed to expand until the pressure is equal to 15 psi. What is the volume that the air occupies? We begin by jotting down Boyle's law. And in this example, we have a P1 and P2, and we have the V1. And the V2 is the unknown. We plug the values in to solve 28 liters. Let's see that we cancel out the PSI units, and we're left with liters. And all along, we have two significant figures. Charles' law states that at a constant pressure, the volume of a gas is directly proportional to its temperature. Now, if the temperature goes up, the volume goes up. If the temperature goes down, the volume goes down. Mathematically, we represent that relationship as V is proportional to T. In the mid-19th century, William Thomson, who was later granted to be Lord Kelvin, compared plots of volume versus temperature for a number of gases shown here. Although he could not measure gas pressure at very low temperatures at the time, Thomson observed that the relationship continued to decrease in a straight line manner. The temperature of 273.15 is absolute zero, the lowest possible temperature. And this came out of his collection of carefully constructed data relationships. And we call this absolute zero, the temperature at which theoretically particles of material have zero kinetic energy. And from this relationship, it was established that minus 273.15 degrees C is considered absolute zero, the temperature at which kinetic energy is zero or motion ceases. 0 degrees K. So in converting from degrees C to degrees K, we would add 273.15. We commonly use Charles's law to predict how volume of a gas will change with temperature, or vice versa. Because V over T is a constant, we could say that V over T1 equals V2 over T2. And working with Charles' law problem, you can use units of constant units of volume, but you must express temperature in degrees Kelvin. Let's look at an example here. A balloon has a volume of 3.2 liters at room temperature, 25 degrees C. Inside the balloon is heated to 100 degrees C. What's the new volume? So in this example, we write down information we have and what we want to find. Convert the temperature to degrees Kelvin. And now use the relationship from Charles's law and solve for V2. And degrees K cancel out, and we will arrive at the answer of 4.0 liters. In many situations, the pressure, volume, and temperature of a gas all change together. For example, in an air-conditioned system, these rely on compression and expansion of gases. As the gases and volume of the gas change, the temperature also changes. For situations like this, we use a combined mathematical relationship called the combined gas law. As in Boyle's and Charles's law, we can use units of pressure and volume, just staying consistent, but temperature, again, must be expressed in Kelvin. And here's another example. A gas with a temperature of 280 degrees Kelvin and a pressure of 200 kilopascal and a volume of 25.8 liters is compressed to 15.8 liters, causing the pressure to increase to 350 kilopascal. What is the temperature of the gas under the new conditions? In this example, we're given several values. We pull them out of the question, and we're asked to solve for T2. We begin with the combined gas law relationship, then we can rearrange for T2. Plug in values, cancel out units, and arrive at the new temperature. The pressure, volume, and temperature of an ideal gas relates together through simple relationships. So we looked at Boyle's law, Charles's law, and combined gas law. Finally, we look at two more laws, and they are Avogadro's law and the ideal gas law. And we'll take a look at mixtures of gases and consider molecular explanation for the gas laws. Avogadro's law, and you should remember Avogadro, where he's related to the mole, description of the mole. And if pressure and temperature is constant, the volume of a gas is proportional to the number of moles constant. The more gas present, the larger the volume that the gas occupies. Mathematically, we could say that the volume is proportional to the number of moles of gas. And this number turns out to be 22.4 liters. 1 mole of gas will occupy at standard temperature and pressure. This is about the volume of a large balloon, the one shown there. The gas laws described so far allow us to relate different properties of gas. We could connect these together using the ideal gas law. The extraordinarily useful law relates the amount of gas present at a given pressure and volume and temperature. And we write this as PV equals nRT, P being the pressure, V being the volume, and the number of moles, T the temperature, and R a what's called universal gas constant. Again, T must be in Kelvin, and the units used for pressure must be consistent with the gas law, with the ideal gas constant, the gas constant. So let's look at an example. What volume does 1.00 mole of gas occupy at a temperature of 0.00 degrees and a pressure of 1.00 atmospheres? If you're watching closely, you may already know the answer to this one, but let's work it through. We begin with the ideal gas law, and our temperature must be in degrees Kelvin. And we are asked about volume, so we'll make that solve for volume. We use the gas constant. You can see how units cancel out, and we are left with volume. And that volume is 22.4 liters. That's what we expect from 1 mole of gas at standard temperature and pressure. Most commonly, we naturally encounter gases that are mixtures. For instance, air is 78% nitrogen and 21% oxygen, and a little more of some minor amounts of other substances. But the partial pressure, this is the pressure caused by each of those gases in the mixture. Fortunately, when dealing with ideal gases, the pressure and volume depend only on the amount of the gas present, not on the identity of the gas. So 1 mole of oxygen gas has the same pressure of 1 mole of nitrogen gas, or even a mole of carbon dioxide gas, one of the other minor constituents of air. So when working with mixtures, we sometimes call this a partial volume problem. So let's look at an example. if a 40.0 liter cylinder is filled with 5 moles of nitrogen, 2 moles of oxygen, 3.00 moles of carbon dioxide, at a temperature of 400 degrees K, what's the pressure inside the cylinder? So there are two approaches that we can use for this problem. First, we calculate the pressure of the individual gases and add those together. Like this. Each of them contribute partially to the overall pressure. And we'd add those together and come up with 8.21 atmosphere is what the pressure would be inside that cylinder. Alternatively, a second approach could be to add up the moles, total moles of 10. And as we said, it's independent of the identity of the identity of the gases. So the moles we can sum together and solve and come up with the same result. So overall, we've seen that there are a number of mathematical relationships, and these are usually you'll have them provided to solve any problems or in a quiz or a test. And we can use these to predict the behavior of a gas. So how does for instance, how does the pressure change if the temperature of a gas increases? At high temperatures, the particles move faster. So if we think of this at a molecular level, this is our theory of why that pressure increases. On the other hand, if we slow down these molecules of gas by lowering temperature, there's less collisions with the surfaces of the container, and if a lower pressure. If we add more gas, there's going to be more collisions and higher pressure. Another concept is the spread of particles through random motion, and we call this diffusion. Diffusion refers to either a liquid or a gas state, but the principle is the same. Particles randomly move, and as they do, they slowly spread out. For example, gases emitted from a smokestack diffuse out into the atmosphere because lighter particles move quicker than the heavier particles. The lighter gases diffuse more quickly than the heavier ones. Effusion is the process of a gas escaping from a container. Like diffusion, the velocity of the gas particles differ with their size. For example, in this image, the two containers filled with helium, one with air. Each container has a small hole out of which the gas can escape. The smaller helium particles, individual atoms as opposed to diatomics, shown with the CO2 and nitrogen, will escape more easily and faster. As a result, more likely to encounter the opening and leak out of the container. So we see this principle of a fusion in ways that balloons lose their gas. If we fill rubber balloons with helium and another with nitrogen and another with argon, we will see the balloon filled with the lightest gas, helium, deflate faster. And for this reason, helium balloons typically, to make them last longer, use less porous materials. And finally, on a bigger scale, sudden changes in gases have explosive results. The changes are often when gases formed and consumed in chemical reactions. The safety of conduct of reactions involving gases, we must know how much gas is produced and consumed, the important job of chemical engineers. To conduct reactions safely, it is needed to be aware of how much gas is being produced in a chemical reaction, and as well as the temperature. For example, in a fermentation reaction, how much CO2 is produced from a kilogram of glucose when it undergoes a reaction of fermentation? The answer to this question, we refer back to stoichiometry and also the laws of the gas laws that we've seen here. So let's look at this example. And here's how we relate the gas laws. In the center of the two concepts is, of course, the mole and mole ratios that we've learned before. And on top of that, we can, if we get certain kind of question, we can overlay what we just learned about gas laws. So we'll go through this example, but this is a bit beyond the scope of our study here in our course. The fermentation of glucose, how many moles of carbon dioxide are produced from a kilogram of glucose that reacts if the reaction takes place in a sealed container and the gas occupies a volume of 8.10 liters at a temperature of 21 degrees C. Find the pressure of the carbon dioxide inside the container. To solve this problem, we first need to relate grams of glucose to moles of carbon dioxide. And we've done similar problems to this point. So we begin with 1,000 grams of the glucose and the molecular weight of glucose to convert into moles. And we then, the stoichiometry of the equation is two moles of CO2 per each mole of glucose. And we do our dimensional analysis, canceling out along the way. We find that there's 11.10 moles of CO2 produced from that amount of glucose. And now we use the ideal gas law and convert and find the volume that CO2 will occupy, 33.1. The pressure that CO2 will exert on the container. Now let's do one more example. Natural gas burns cleanly. If it burns cleanly, methane with oxygen to produce CO2 and water. If 13.1 liters of methane burn at a pressure of 1 atmosphere, 1.00 atmosphere, and a temperature of 290 degrees K, what mass of carbon dioxide is produced? In this question, we're given the pressure and volume. Our first step is to convert this to mole. Using ideal gas law. We have 0.550 moles of methane. Once we have the moles of methane, we can use the balanced equation and relate the methane to CO2. And once we have moles of CO2, we can convert the moles to grams of CO2. It comes out to 24.2 grams of CO2. So in these examples, we use the ideal gas law to relate the pressure, volume, and volume to moles of a substance. Once we have the moles, we can relate the moles to any other substance in the equation using the balanced equation. And we'll stop here.